Dear students, so welcome to the next lecture of microcontrollers. Today we will cover arithmetic and logic instructions. So let's move on. So the first thing that we have in our agenda today is the addition of unsigned numbers. So this instruction you have probably come across so far when you are doing different assembly language coding. So you are adding a number, okay, which is denoted by this source. This source can be a direct number or some number stored in some registers, and then you are adding the numbers inside the accumulator. In fact, you are adding the number with the content of the accumulator, so the actual operation is like this. And the destination operand is always in register A, so this is important. You have probably come across this concept before. Source operand can be a register or an immediate data or in memory, as I just said. And memory to memory arithmetic operations are never allowed, okay, in 8051 assembly language. So you have to bring the data wherever they are in the memory to your accumulator to do this arithmetic operations of addition. Okay, so for example, you have two numbers that you are adding, and basically when you are adding, the different flag that are there in the flag register or PSW register, they get modified differently. So so let's see this example where you are adding these two numbers F5 and 0B. So basically the actual addition is 0 0, so this is the binary equivalent. So you are doing this addition, so you're moving the first number to accumulator and then adding the next one with the accumulator. This is a pretty straightforward syntax. So let's see how the different flags will be changed. So carry will be 1 since there is a carry out from D7. So basically you have 0 0, but then there is a carry, okay, and you have all the 8 bits as 0 0, so there will be a carry here. So the carry flag will be equal to 1 because you have a carry from D7. The parity flag will be also 1 because the number of ones is 0. The auxiliary carry will be also 1 since there is a carry from D3 to D4. So you add these two numbers. Let's say this is 0, and then the 1 carry is brought here, so you have 0 here. The 1 carry is brought here, so you have 0 here. And then the 1 carry is brought here, then you have 0 here, and then another 1 carry comes here, so there is a carry from D3 to D4, so therefore the auxiliary carry will be also equal to 1. So you can use these instructions, and you can add individual bytes, okay, that can be stored in different locations in your memory, okay. And if your sum is more than 8 bits, obviously if you are adding a lot of numbers, let's say the 5 numbers here, all of them being 8-bit numbers, or a single byte long number, then the chances are high that when you are adding these numbers, the resulting sum will be more than 8 bits, and there should be some some arrangement to account for that, okay. So basically this example shows how to handle this type of situation. So let's say you have RAM locations from 40 to 44H, so you have 5 RAM locations that have the following values, okay. So there are these 8-bit or a single byte number, Write a program to find the sum of all these values. At the end of the program, the register A should contain the low byte and R7 should contain the high byte. So after adding all these numbers, whatever be the addition, okay. So if I add all these number, then whatever be the addition, okay, that should be contained in A and R7. So A will contain the low byte, uh, and R7 will contain the high byte. Okay. So let's see how to deal with this. So for example, you are loading the register R0 with 48 and you are loading register R2 with 5. So you have the initial location of the RAM that is initialized here in register R0, and then the number of locations is 5, so you have R2 initialized to that number or the counter, and then you are clearing the accumulator to make sure that there is nothing, no residual value there. Then you are also clearing R7, so to make sure that there is no residual value, so R7 and A, they will contain your final addition, so you are clearing them. So now you are adding the contents of R0 with A. So at R0 you have 48. Basically you are adding the contents of the memory location pointed by R0. So what does that mean? R0 contains 48. So whatever is there in memory location 48, which is this number 70, that will be added to your accumulator. So at this stage, your accumulator will contain accumulator plus 70. Okay, so initially it was 0, so in that case your accumulator will be 70. Then you are checking the carry flag. Okay, so if your carry is 0, which means there is no overflow, then you don't do anything, so jump on no carry. So if there is no carry, then it will go to this line next, where you are incrementing R0 to get the next value, because R0 is initialized at the first location of the RAM. So if after this addition, if you don't have any carry, you increment R0 to point to the next location, so that you can add the next number with 70. Okay, the next number being this one in the next location. So you have to increment R0, and then you repeat this process 5 times. So DJNZ R2, where R2 contains 5. So you decrement R2, it goes to 4. So it's not 0, so therefore it will go to this line, which is this, where you are adding the current value in the accumulator with whatever your R0 is pointing at. So at this stage you will have accumulator equal to 7D plus EP. Okay. Now again you check for carry. If there is no carry, then you go to this step again. But if there is a carry, let's say, then you increment R7. So if there is a carry, you keep on incrementing R7. Let's say after these two addition there is a carry, so R7 will be 1, and accumulator will contain the 8 bits and the corresponding to this addition, ignoring the carry. Okay, and then if you keep repeating this process, then after you are done 5 times, it will add all these values. Okay, and whenever there would be a carry, it will increment R7 so that R7 contains the high byte. Okay, so um, and A will finally contain the low byte. Okay, so that is the arrangement here, and you are using the add instruction here uh, for doing this operation. So other than add, you have this add C instruction. So here you can directly add you know um, 16-bit numbers. So we can use this add C instruction for addition of 16-bit numbers. So in the previous case, when you saw that when we were using the add instruction, sorry, so when we were using the add instruction, we had to take a note of the carry flag, right? So just for the previous example, if you see, when we were adding the numbers, we were keeping a track of the carry flag. Okay, so if the carry was 0, then don't add carry. So if JNC next, so we were directly going to the step. So there was an arrangement to you know track the carry flag, right? So in case of your add C, you can directly add two 16-bit numbers. Okay, and the carry, okay, is um, is automatically taken care of. Okay, so basically when adding two 16-bit operands, let's say the propagation of a carry from lower byte to higher byte is constant. So when the first byte is added, um, you know only, let's say, these two, E7 and 8D. So these are two 16-bit numbers, by the way. Okay, and when the first two bytes are added, okay, there is a 74, and then there is a carry. Okay, the carry is propagated to the higher byte, which result in 3C plus 3B plus 1 equal to 78. So earlier, as you were seeing, when we were adding let's say 8-bit numbers, okay, and then if there was a carry, then we were storing the MSBs in, let's say, another register R7, and the final result was stored in A, as you saw in the previous example. Okay, so A should contain the low byte and R7 should contain the high byte. So in this case, if you're using add C, you don't have to do this. You don't have to store them in two registers. Okay, I mean, you have to store them in two register. I'm sorry, because you are adding 16-bit numbers, so definitely you have to store them in two registers, but you don't have to keep track of the carry to increment the higher byte. Okay, if there is a carry, you are incrementing the higher byte by 1, and so on. That you don't have to do if you are using add C. So let's see this example. Write a program to add two 16-bit numbers. Place the sum in R7 and R6. R6 should have the lower byte. Okay, so here you are first clearing the carry flag. Okay, and then you load the lower byte, okay, to your accumulator. So and then add the other corresponding lower byte to the accumulator. Okay, and then you save the low byte sum in R6. So you just directly move this to R6. Okay, so you have added these two number and you got, let's say, 74 here. Your accumulator will contain 74, and 74 will move to R6. But then there was a carry also. Okay, so if you add these two lower byte number, the carry flag will be set to 1. Okay, so now you are moving the higher byte 3C. Okay, and then you are adding, instead of a regular add, if you use add CA with the other byte, then this carry will be automatically taken care of and added together with these two numbers, and then you have the higher byte which you are saving in R7. Okay, if you are using add, just add, then you have to check whether the carry flag had been set to 1 from the previous 2 bytes addition, and then probably you have to use an instruction like JNC, just as you did for the previous one. Okay, so this is the case. So you are using add C, and usage of add C is directly taking care of the carry flag in the background. You don't have to write a extra line of code to monitor the carry flag and then add it to the high byte numbers. Okay, so that's the utility of add C instruction. Now let's focus on the BCD number system, and then we will see how you can add BCD numbers. Okay, some instructions that we are going to learn next. So BCD, as you know, the term means binary coded decimal. So the binary representation of the digits 0 to 9 is called BCD. Okay, so you have here 0 treated as a as a nibble of 4 bits. 0 0 0 0, 1 is 0 0 0 1. In that way you have up to 0 to 9, which is coded as binary coded decimal as this. Okay, so you can have unpacked BCD and packed BCD. So in case of unpacked BCD, the lower 4 bits of the number represent the BCD number, and the rest of the bits are 0. Okay, so you represent unpacked BCD as a byte. Okay, and the lower 4 bits represent the BCD number. Let's say in this example this is 9, and these are all zeros. Okay, uh, in this case also the lower 4 bits signify 5, and then these are all zeros. Okay, so this is unpacked BCD for you. For packed BCD, a single byte has 2 BCD number in it, one in the lower 4 bits and one in the upper 4 bits. Okay, so this is a packed BCD for 5 9 hex. Okay, so you have 5 in the upper BCD and 9 in the lower BCD. Okay, so this is called packed BCD. So so adding two BCD numbers must give a BCD result. Okay, so let's say if you add these two numbers, then adding these two numbers directly in binary will give you this result. Okay, which is not in BCD. So 1 7 in BCD means this thing. Okay, if you consider a packed BCD example, so this is your 1 7. Okay, and then 2 8 will be this in packed BCD. Now if you add these two numbers, then the result has to be 17 plus 28. I mean both are in hex, so the result has to be 4 5, which should be this. Okay, but if you add this two numbers, the microcontroller won't distinguish whether this is a BCD or just regular binary 8-bit number. So it will just add bit by bit, and it will give you this number. So this is actually if you just try to comprehend it as a BCD, then you will comprehend it as 3F. Okay, instead of 4 5. Okay, so there is a mismatch. So to correct this problem, the programmer must add 6 or 0 1 1 0 to the low digit. Okay, so if you add 0 6 to 3F, then you will get 4 5. Okay, so basically if you have this number, okay, um, Let me rewrite it once again. So if you add 0 1 1 0 to the lower bit, then you will get um, sorry, let's say 1 0, this will be 1, this will be 0 0. So this will be 4 5 in hex. So this adjustment has to be done. Okay, and to do this adjustment, you have this special instruction called decimal adjust, or DA. So if you do DAA, then it just adjusts the addition uh, in the accumulator. Okay, so the DA instruction is provided to correct this problem associated with BCD. So it will add this 06 to the lower nibble, or let's say 6 to the lower nibble, or even higher nibble if needed. Okay, just to make it BCD. So let's see this example where you are adding two numbers 4 7 and 2 5. So then these are BCD operands. So you are adding these two numbers. Okay, and the hex equivalent after this addition is 6C, but you have to make this 7 2 to make it BCD. So you have to make this adjustment, and this after this addition, which gives you 6C, if you use this instruction DAA, then whatever value that's in the accumulator after this line, which is this, 06 will be added to it to make it BCD equivalent. And the DA instruction works only after an add, but not after an INC. So you have to be careful about this. If you are using an increment A, which just adds, 1 to the contents of the accumulator, if you use this, then after this you cannot use this. Okay, so this is not possible. So yeah, so therefore you have to be careful that the DAA works only after an add. So if you are using it after an increment, it won't use. But if you still want to make it use, then instead of increment, you just say add A. Instead of increment A, you just say add A with 1. Okay, and then you can use the DA. So in case you want to use DA after adding, let's say, 1 to your accumulator contents, you cannot use increment, you have to use add. And the DA instruction works only on accumulator. In other words, while the source can be an operand of any addressing mode, the destination must be in register A in order for this DA instruction to work. Okay. So after an add or add C instruction, you can use this DA instruction, and what it does is that if the lower nibble is greater than 9, or if your auxiliary carry is equal to 1, then you would add 0 1 1 0 to the lower 4 bits. If the upper nibble is greater than 9, or if your carry equals to 1, then you add 0 1 1 0 to the upper 4 bits. So this is again a very important piece of information. So if your auxiliary carry is 1, you add 0 1 1 0 to the lower 4 bits. If your carry is equal to 1, you add 0 1 1 0 to the upper 4 bits. Okay, so so this is what is happening. Okay, here if you do this addition, here since auxiliary carry is 1, after the addition DA will add 6 to the lower nibble and you will get this number. Okay, so this is the binary sum. Okay, here you can see that there will be an auxiliary carry after this step. Okay, you can verify. So you are adding this 0110 to the lower nibble and then you get the adjusted BCD number. So let's see an example of the DA instructions. So let's see the same code, or rather the similar example of adding 5 numbers. In this case they are BCD numbers from RAM location starting from 48. So we did a similar, you know, we did a similar example. So let's see what will happen. So you are loading your R0 with 40H, you are loading R2 with 5. So these are the two initial loading parameters, and then you are clearing A and R7. Okay, and then you have so in this case let's see how your decimal adjust will be working for adding 5 BCD numbers. So you are initializing R0 and R2 similar to the example that we saw before. You are clearing A and R7 by these two lines, and then you are adding as usual the first number that is in R0, which is this one, and then you are doing the decimal adjust immediately here in this line, and then if there is a carry, okay, then you go to the next line, which is incrementing R0. Okay, if there is no carry, okay, then you keep track of the carries by incrementing R7. Sorry, if there is no carry, yeah, you are going to the next step, but if there is a carry, then you are incrementing R7, and then you are repeating the operation again. Okay, so the difference between the previous example of adding 5 numbers and in this example of adding just 5 BCD numbers, the only difference is that after every addition you are doing this decimal adjust step. Okay, so just to count for the BCD operation. So at this addition stage, okay, if there is an auxiliary carry, okay, then as you saw what this what decimal adjust operation does, it will add 0110 to the lower nibble. Okay, if there is a carry, then it will add this number to the higher nibble. Okay, and then this carry is still there. Okay, that carry is getting tracked off, and then you are incrementing R7. Okay, so basically your final BCD number will be in A and R7. Okay, combined together. Okay. So R7 will contain some part of it, and A will contain some part of it. So the final addition will be a 16-bit BCD. Okay, so then that's why your A will contain the 8-bit BCD equivalent, and R7 will contain the other 8-bit of the BCD equivalent here. So the summary is that the only adjustment that you are doing because it's a BCD addition, is this decimal at just A. Okay. So now we move on to the subtraction of the unsigned numbers. So in many microprocessors there are two different instructions for subtraction. You have subtract, just the regular subtraction, and then you have sub B, which is subtract with borrow. So in your 8051 we only have sub B. Okay. So so in that case, your sub B, what it does is that if you're using sub B with A and the source, so these are the two operands, one is in A and the other is the source, then what it does is that actually A minus the source minus any carry that would be generated. Okay. So to make sub out of sub B, we have to make the carry equal to 0. Okay. So if this carry is 0, then this part is redundant, and then we have just A minus source, which is the regular subtraction operation. So you notice that we use the carry flag for the borrow. Okay. So here is an example, subtraction of unsigned numbers. So when you are doing subtraction of unsigned numbers, your carry is equal to 0. You take the 2's complement of the subtrahend and add it to the minuend, which is in A, and then you invert the carry. Okay. So so you have this piece of code which is subtracting 6E from 4C. Okay. So 4C minus 6E will give you minus 22. Okay. So here in this case, you are first adding the numbers here. So this is your 4C. Okay, and you are adding the 2's complement of the subtrahend. Okay, so this is your subtrahend. You are taking the 2's complement here, and then you are adding these two numbers, and whatever you have, the final bit here signifies the carry. You just invert the carry to make it 1. So if your carry is 0, the result is positive. If your carry is 1, the result is negative, and the destination has the 2's complement of the result. Okay. You can have subtraction of unsigned numbers. So you are using sub B when your carry is equal to 1. This instruction is used for multi-byte numbers and will take care of the borrow of the lower operand. So let's say you are doing this type of operation where you have 16 bits. Okay, so you are subtracting this 16-bit number from the other 16-bit number. So in that case, you first work with the lower 2 bytes. So 62 is the lower byte here, and 96 is the lower byte. So in this case, if you do 62 minus 96, you will have CC hex with a carry equal to 1. Okay. So you save the result. Okay, you save this CC in R7. Okay, and then you are moving the higher 2 bytes. I mean, you are operating on the higher 2 bytes. So your A will have now 27 hex, and then you are subtracting 12 hex with carry by this sub B operation. Okay, so this will do 27 hex minus 12 hex minus 1, so you will have 14 hex, and then you are saving the result in R6. So finally you will have 1, 4 and CC. Okay, so that will be your result here. Next instruction is unsigned multiplication. So in this case you have this mul AB. So this does A multiplied by B, and the result is obviously 16-bit, because if you are multiplying two 8-bit numbers, then the chances are that the result is 16 bit. Okay, so the result will be both stored in B and A. Okay, so you have A equal to 25H, okay, and B equal to 65H, let's say. If you are doing mul AB, which is multiplication of these two numbers, then you have the 16-bit result, which is E99. So the A will contain the low byte and B will contain the high byte. Okay, so you have A low byte and B high byte. Okay. You can similarly have an unsigned division. So in this case, the 8051 will use this instruction, which is DIVAB. So in this case, you will just divide A by B. Okay. So here you are loading one number 95 in A, another number 10 in B, and if you are doing divide AB, then your A will contain the quotient, which is 9, and B will contain the remainder. Okay. And the carry is always 0 in this case. Okay, but the overflow flag will be in use here. So if your B, the denominator is not equal to 0, then the overflow is 0. But if your denominator is 0, then the overflow will set to 1, indicating an error, because you cannot divide by 0. Okay, that is undefined. So let's see how we are applying the division operation. So let's say we take this example where we have to write a program to get hex data in the range 00 to FF from port 1 and convert it to decimal. So, and then you save it in R7, R6 and R5. So let's see how this works. So assuming that P1 has a value of FDH for the data, analyze the program. Okay. So the first step is to configure this port P1 as an input port. So as you know from your previous lectures, that you have to move 0FF to the port to make it an input port. Okay. Now you read data from port 1 and bring it to your accumulator. Okay. You move 10 to your B register. Okay. And if you do divide AB, then basically whatever number is there in A, that is getting divided by 10. Okay. So B will contain your lower digit. Okay. So you are saving that in R7. Okay. Now you again move 10 to B and do the division again, and then your B will contain the lower digit again, and that will be saved in R6, and finally the whatever is remaining in A, that will be saved to R5. Okay. So so when we are doing these divisions, in case of your binary, in case of your decimal to binary conversion also, what you usually do, let's say you take any decimal number, let's say 50, and then you are doing repeated division by 2, right? So if you do this division, then the quotient is 7 and then the remainder is 1. Okay. Then you do another division, the quotient is 3 and the remainder is 1 again. You are doing repeated division by 2. Okay, so in this case you will have a remainder 1 and then finally it stops. So your binary number will be 1 1 1 1, equivalent to 15, right? So similarly here also, when you are converting these numbers, whatever input you are getting from port 1, if you want to convert it to decimal, you are doing repeated divisions by 10. Okay, so these are the 3 steps. So if your number is, let's say, FD, okay, then if you are doing this division, 1 division by 10 will give you quotient of 19 and the remainder of 3. Okay, then you again do the same division, you will get a quotient of 2 and the remainder of 5, and then finally you have this digit. So if you read from backwards, you will get 253. Okay, so these individual digits are stored in different registers. So R7, R6, and R5. So if you see R5, R6, and R7, you will get 2, 5, and 3. Okay, so this is how you can apply uh, the division operation, and you can convert, let's say, a hex number or a binary number to decimal by repeated division by 10. So so this is one application of division. The next instruction that we will see is 2's complement. So to make the 2's complement of a number, what you do is simply take a complement where you get the 1's complement, and then you add 1 to that, so you get the 2's complement. So this complement operation can be used to have this 2's complement. So this is another new instruction that you have learned just now. So next we have a set of logical operations, logical instructions. So the logical AND can be implemented using this ANL instruction. So if you have a destination and a source, this ANL instruction will just do the logical bit by bit AND of these two numbers. Okay, so let's say if you have 3 5 hex and 0 fx, then whatever 3 5 stands for in binary and whatever 0 5 stands for in binary, you have a bit by bit logical AND operation. So each individual bit will be ANDed and the result will be 0 5 hex. Okay, so this ANL is often used to mask certain bits of an operand. Okay, you will use this operation in some of your labs. Okay, so and then you will see the application of this logical AND operation. Similarly, you can do logical OR also. So same logic applies here. Whatever be your individual numbers, you just do bit by bit OR when you are using this ORL instruction. And ORL instruction can also be used for certain purposes. For example, to set certain bits of an operand to 1. Okay, so again you will see the application of this logical OR in your labs. And then finally we have logical XOR. So again, similar to AND and OR, you can do bit by bit logical exclusive OR using this XRL instruction. Okay, so XRL instruction can be used to toggle certain bits of an operand. So let's say if you want to just toggle these 4 bits, okay, so you can set a certain combination where the corresponding bits of these 4 bits will be 1, and if you do an XOR with 1, then basically it denotes a toggle operation. So you can toggle a certain number of bits from an entire byte by making this arrangement and then using the XRL instruction. So the XRL instruction can be used to clear the contents of a register also. Okay, so if you XOR with itself, then you will get all zeros. So you can do clearing of the contents of a register by doing a bit by bit XRL with the same number. Okay, so let's see an example. Read and test P1 to see whether it has the value 45 hex. If it does, send 99 hex to P2. Otherwise, it stays cleared. So here you can use this logic. Okay, that your ORing with the same number, so you have to check whether it is 45H or not. So you can do a logical XRL with 45H, and if your accumulator, which will contain the final result of the XR operation, if that is all 0, then you can perform the next step. So you can have an arrangement like this J and Z, which means jump if your accumulator is not 0. Okay, so if the number is not 4 5, okay, then it will be not 0, and then it will go to the next step. Okay, if it is 0, then it will go to the exit step. Okay, so if both registers have the same value, 0 0 is placed in A, and then JNZ and JJs can be used to test the contents of the accumulator and then perform the next step. Okay, so here in this example, the next step is to move 99 hex to P2. Okay, so here you are checking whether your accumulator is 0 or not by using this J and Z operation, and if it is 0, which means that the number that you are reading from port 1 is indeed 45H, then in that case you go to the next line and move 99 hex to port 2. Otherwise you just exit and do whatever this exit line signifies. Okay, so this is equivalent to if else or type of logic in a high level language like C or Java. You are using this J and Z exit to check if the number that you are getting from port 1 is equal to 45 hex or not. Okay, so then you do something which is moving 99 hex to port 2, or else you do something else which is denoted by this exit level. Okay, then the next instruction that we will study is the compare instruction. So again, here you have 3 operands here. Okay, so you have a destination, you have a source, and then you have a relative address where this jump will occur. So CJNE actually means compare and jump if not equal. Okay, so it will compare the two numbers in the destination and source, and if they are not equal, then it will jump to this line signified by this relative address. Okay, so so let's see. So the CJNE instruction compares two operands, as I just said, and jumps if they are not equal. The destination operand can be in the accumulator or in one of the registers, okay, R0 to R7. The source operand can be a register or a memory or can be an immediate number. Okay, and the operand themselves remain unchanged. Nothing happens to the operands. Their values are compared whether they are equal or not, and then it jumps to a specific address. So if the operand doesn't change, then what changes? Based on something, some condition, the jump has to take place, and actually in case of this CJNE instruction, the carry flag actually changes. So the carry flag changes to indicate if the destination operand is larger or smaller. So basically CJNE is checking whether they are equal or not. If they are not equal, then a jump will be performed, and if two numbers are not equal, then the other two possibilities can be either one of them is larger or smaller to the other, and if it is larger or smaller, depending on that, your carry flag will be 0 or 1. Okay, so if your destination number is greater than the source, greater than or equal to the source, then the carry flag will be 0. If the destination number is less than the source, then the carry flag will be 1. And again, you can use this in a code to do some comparison. So let's say you are comparing the contents of your register R5 with the number 80, okay, and if they are not equal, okay, then it goes to this line which is labeled by not equal, okay, and when they are not equal, then you have to check for the other two possibilities, if it is greater or if it is lesser, okay. So let's say if it is greater, then your carry flag will be changed, okay. So if it is greater, if it is greater, then your carry flag will not change, so your carry flag will be 0, and then you can use this jump on no carry and move to this line denoted by next. So if your R5 is greater than 80, then you do whatever logic that is denoted by this line next. If your R5 is less than 80, then it goes to the immediate next line where the logic required for this particular condition less than 80 will be performed here, okay. So see, we have three conditions. R5 can be equal to 80. If your R5 is equal to 80, then this is the line where the instruction operates for R5 equal to 80. If not, then it can be greater than 80. So for greater than 80, this is the line where the logic related to greater than 80 will be performed, and you are using J and C to jump to this line because your carry will be 0 if your R5 is greater than 80. And if your R5 is less than 80, then this is the line where you are performing the logic associated with R5 less than 80. Okay, so basically if you have a flow chart, let's say like this, and then you are checking if your R5 is equal to 80 or not, okay. So if this is yes, okay, if this is yes, then it's going to this line, okay, of your code, whatever is the logic associated with being R5 equal to 80. If it is no, then the next step is to check whether it is greater than 80 or not, okay. If it is greater than 80, if this is yes, then this is the line for checking for performing the logic associated with greater than 80. And if it is not greater than 80, let's say if your answer is no here, then this is the line which is the logic associated with R5 less than 80. So see how you can use CJNE and other logical jump instruction like J and C to perform three conditions together, whether R5 equal to 80 or greater than 80 or less than 80. The next instruction that we will study is rotate right. So this is denoted by RR. So this basically rotates the bits of the register A from MSB to LSB, and then the least significant bit which is coming out of this register because of this rotation becomes the most significant bit, okay. So this is a circular shifting operation that is happening, and the shifting is going from left to right, from MSB to LSB. So you can do, let's say, this type of operation where you are moving this number 36 to your accumulator, and then you can do 4 rotation, okay, to completely invert the number. So this is 63. So 36 is swapped to 63 by using, let's say, 4 rotate right operations, okay. So these type of things you can perform using rotate right. You can also use rotate left, where the rotation is taking from right to left or LSB to MSB, and whatever is coming out through this MSB is it becomes the LSB. So again, this is a circular shift, and bit D7 exits from MSB and enters into D0. So here also you can do similar functionalities using rotate left. You have this number 72, and you can do rotate lefts, okay, and then you will have this final result, okay. Then you can also have rotating through carry, okay. So this is rotate right through carry, so this is RRC. So basically here in this case the rotating will happen through the carry bit, okay. So the shifting starts from MSB to LSB. Whatever comes out of the LSB, that goes to the carry flag, and then again it comes out of the carry flag and then goes to the MSB. So this is an example where you can see that how rotate right through carry operates. So this type of instruction you can use to keep track of, let's say, the number of ones in a bit, okay. Every time you have a bit that is shifted to the carry flag, you can check whether it is 0 or 1, okay. And let's say if it is 1, then you increment a counter, okay. So the number of ones in this bit will be counted in this way, okay. You can have many other application of this RRC. So we will do some examples, and I will ask you to solve some problems also using this. So when you will be solving those, you will be able to appreciate the working of this RRC. Similarly, we can have RLC. So this is rotate left through carry. In this case, the shifting operates from LSB to MSB, and whatever comes out of the MSB goes through the carry flag, and then it goes to LSB. So as I was saying, write a program that finds the number of ones in a given byte. You can use this RRC or RLC and do that. So let's say here you are initializing the count to 8, okay, because you have 8 bits in a byte, and you are counting through all the 8 bits to check how many ones are there, okay. So let's say your example byte is this 97 hex, okay. You are moving that to the accumulator, and then you are using the RLC operation, or rotate left through carry, okay. And every time you are checking the carry, okay. So if you have a carry, then you increment a register R1, which is initialized to 0. So every time there would be a carry because of this RLC operation, the carry will be basically because of a bit 1 in this entire byte, okay. So that presence of bit 1 will be counted by incrementing your register R1 here, okay. If you don't find a carry, or if the bit is 0, then you just jump to this line, okay. And this line is basically moving through the counter, okay. So R7 is getting decremented, and you are repeating this entire steps 8 times, because you have 8 bits in this byte. So we'll stop here today, and then I will see you in the next video lecture.